Welcome to this explainer. Today, we're going on a bit of a mind-bending journey. We're going to be exploring the arrow of time, diving into the ultimate mystery of entropy, gravity, and the Big Bang to figure out why exactly time only seems to move in one direction. Let's get right into it.
Okay, so here's the central mystery we're dealing with. Why does time only go one way? I mean, think about it. Why do dropped eggs shatter into a mess on the floor, but they never, ever spontaneously reassemble themselves back into a perfect egg? Well, here's a deeply unsettling fact from the source material. If you actually look at the fundamental laws of physics, whether that's Newtonian mechanics, quantum mechanics, or even relativity, the equations literally do not care about the direction of time. They work just as perfectly backwards as they do forwards. There is absolutely no mathematical arrow in those rules that says, hey, this way to the future. To really picture this, think about the microscopic scale for a second. If you were to film two isolated particles colliding and then play that recording backwards, you genuinely couldn't tell which way time was running. The motion looks perfectly natural either way. But step back to the macroscopic scale, the everyday world we live in, and reality is entirely one-sided. And egg shattering only happens in one direction. So what does this tell us? It tells us something monumental. The arrow of time isn't actually built into the underlying laws of motion at all. We have to look somewhere else to find our culprit.
And that brings us to the real mastermind behind our cosmic mystery: entropy. This was a concept brilliantly fleshed out back in the 19th century by physicist Ludwig Boltzmann. Now, you've probably heard entropy described simply as messiness or disorder, right? But actually scratch that. It's really a measure of how many macroscopic states correspond to the exact same macroscopic description. It is fundamentally all about probability and counting. And once you start looking at time through this lens, the mystery of why things only happen in one direction just becomes a question of what states are rare and what states are overwhelmingly typical.
To make sure we really grasp Boltzmann's key insight here, we need to clearly define two terms. First, a microstate. This is a complete, highly detailed microscopic description of a system. Imagine tossing 100 coins one by one. The exact, specific sequence of heads and tails you get is your microstate. Then you have the macrostate. This is just the big picture, the coarse-grained feature. For example, just looking at the pile of coins and saying, oh, I got exactly 50 heads and 50 tails, without caring at all about the specific order they landed in. Boltzmann's genius was realizing that certain macrostates have vastly more microstates that create them than others. Just to give you a sense of the sheer scale of possibilities we're talking about, think about flipping those 100 coins. The total number of possible distinct sequences, all the different microstates, is 2 to the power of 100. That is a nontillion different possible sequences. It's over 1,000,000 trillion. If you tried to count every single one of these outcomes at a rate of 1 per second, it would take you far longer than the entire age of the universe just to list them all out. And remember, that's just for 100 simple coins.
So when we break down the actual probabilities, a really fascinating picture emerges. The macro state of getting exactly 100 heads corresponds to exactly one single microstate out of that entire non-divillion. The probability is essentially 0. But what about a relatively even mix? If you look at the odds of getting somewhere between 40 and 60 heads, well, that accounts for 96% of all the possible sequences. The evenly mixed state is overwhelmingly typical, while the perfectly ordered state is statistically practically non-existent. Now, let's take that exact same statistical logic and apply it to the real world. This is the absolute heart of entropy. Imagine squeezing all the air in the room you're sitting in right now into one tiny little corner. When you let it go, what happens? It spontaneously spreads out to fill the room. But why? It's not because some fundamental law of physics forces the molecules apart. It's simply because there are vastly, unbelievably more microscopic ways for those gas molecules to be spread out than clumped together in a corner. It's just a game of probability. As systems evolve, they naturally move from rare states to typical states. In our brains, we actually perceive this exact direction, this direction of increasing entropy, as the forward flow of time itself.
But hold on, because this leads us straight into a massive counterintuitive paradox. If the arrow of time dictates that the universe's entropy is always increasing, always moving from special states to typical states, what exactly happens when we hit rewind? If we run the universe backward in our minds, all the way to the very beginning, it means the Big Bang must have been an incredibly, astronomically low entropy state. It had to be unbelievably special and rare for time to even have an arrow today.
Let's trace the cosmic timeline to see how this mystery really deepens. Physicists can actually observe the early universe by studying the cosmic microwave background. This is the ancient, stretched-out radiation left over from the Big Bang. And honestly, this is where it gets super confusing. When we measure this early radiation, it shows a practically perfect, uniform temperature across the entire sky. Now, in physics, a uniform temperature is the unmistakable fingerprint of thermal equilibrium. And for an ordinary gas, a uniform, evenly spread state is actually a state of incredibly high entropy. So, how on earth could the beginning of the universe be a low entropy state if it was perfectly uniform?
Well, here is where we have to completely flip our intuition upside down, because we have to invite gravity to the party. For an ordinary gas in a box, sure, uniform and spread out equals high entropy, but gravity completely rewrites these rules. Gravity is inherently attractive. It actively wants to pull matter together. So from a gravitational perspective, a perfectly smooth, uniform distribution of matter is actually an incredibly low entropy state, simply because it holds this massive, pent-up potential for future clumping and collapsing.
By carefully studying that cosmic microwave background, physicists have actually calculated the entropy of the early universe right after the Big Bang. It comes out to roughly 10 to the 89th power times Boltzmann's constant, represented by K. Now, 10 to the 89 is a 1 followed by 89 zeros. In everyday human terms, that feels like an impossibly enormous number. But remember, gravity changes the entire game. We have to ask ourselves, what does a truly high entropy state actually look like when gravity is the one calling the shots?
The absolute, ultimate endpoint of gravitational clumping isn't a star and it's not a planet. It's a black hole. When enough matter clumps together, it collapses into a dense region of space where gravity is so strong, not even light can escape. And thanks to the brilliant work of physicists like Jacob Bekenstein and Stephen Hawking, we know that black holes carry an unimaginable amount of entropy. It actually scales directly with the surface area of their event horizons. As our source material perfectly puts it, black holes are the true entropy monsters of our universe.
To really prove this point, let's consider some absolutely staggering statistics. Take Sagittarius A star, the supermassive black hole sitting right at the center of our very own Milky Way galaxy. It has a mass about 4 million times that of our Sun, and its entropy is around 10 to the 90th power K. Do you remember the number for the entire early universe we just talked about? It was 10 to the 89. That means this single, relatively modest supermassive black hole contains more entropy than the entirety of the universe did near the Big Bang. And M87, the massive black hole weighing in at 6.5 billion solar masses, it clocks in at an astounding 4 times 10 to the 96 power K. It's just mind-boggling.
Because practically every large galaxy in the observable universe has a supermassive black hole lurking at its center, they utterly dominate the cosmic math. When physicists estimate the total entropy of our observable universe as it exists today, they arrive at roughly 10 to the 104th power K. This massive, astronomical increase from the Big Bang's 10 to the 89 is driven almost entirely by the presence of these supermassive black holes. The universe is clumping together, and because of that, its entropy is absolutely soaring.
But that begs the question, just how high could it go? Well, gravity gives us a very clear, definitive answer for the maximum possible entropy our patch of the universe could ever achieve. If we were to take absolutely all the mass in the observable universe and collapse it down into one single, gigantic, universe-sized black hole, the entropy would reach an unbelievable 10 to the 123rd power K. That is the ultimate ceiling. That is the absolute highest entropy state that gravity will allow.
Let's just summarize this extreme escalation of scale for a second, because it reveals the true depth of the mystery we're exploring. The maximum possible entropy is 10 to the 123. Today's entropy is around 10 to the 104, and the Big Bang's entropy was just 10 to the 89. When you compare what the early universe was to what it theoretically could have been, you realize it wasn't just low entropy. It was absurdly, fantastically, unbelievably smooth and finely tuned. It sat a full 34 orders of magnitude below the maximum value that gravity allowed.
So, here is the absolute crucial takeaway. The Nobel Prize-winning physicist Roger Penrose actually calculated the exact probability of our universe starting in such a staggeringly smooth, low-entropy state purely by random chance. And it is this giant, almost impossible double exponent fraction, 1 in 10 to the power of 10 to the power of 123. Writing this number out in full would literally require more zeros than there are subatomic particles in the entire observable universe. It means the initial state of our cosmos was special beyond anything our ordinary, everyday intuition can even handle.
Bringing all our cosmic detective clues together, the picture becomes clear. We experience time moving forward because systems naturally, statistically, evolve from rare states to typical states. Entropy increases. But this is only possible because gravity actively dictates what a high entropy state actually is. Because the early universe began in a gravitational state that was ridiculously special and uniform, it left practically infinite room for matter to clump, for black holes to form, and for entropy to inevitably rise. That grand, sweeping cosmic setup is the exact reason you and I experience a forward flow of time today.
Which leaves us with one final, incredibly provocative thought from our source material. If the odds against it are literally astronomical, why was the Big Bang so special in the first place? Was it just some bizarre, lucky fluke of pure chance? Is it a hidden rule of quantum gravity that we just haven't discovered yet? Or is it something else entirely? It remains one of the absolute greatest unsolved mysteries in all of physics. Thank you so much for joining me for this explainer. Keep wondering, keep learning, and until next time, stay curious.